All right, so this is notes F, our last set of notes on acids. This is something called acid deposition. It is the same exact word as deposition in terms of the phase change from where a gas turns directly into a solid, but it has absolutely no relation context-wise, completely different definition. So, next screen. What it's actually referring to is acid coming out of the air, like out of the atmosphere. So the rain itself, like water rain, is a little acidic because it has some dissolved CO2. But when we're talking about acid deposition, we're talking about something that's actually called acid rain, which has a pH that's less than 5.6. So regular rain is a little acidic, but acid rain is the harmful stuff we're talking about today. And then here's just to kind of show you, like, how does CO2 make it acidic? Well, it's because it kind of bonds and forms into a carbonic acid, which then likes to dissociate into bicarbonate and has these H+ ions kind of in the atmosphere. And so that's a problem when it like reacts with rainwater and things and can be carried down into, like, destroy the rainforest, for example. Yeah. So the acid deposition is the process where the acidic particles that end up in the atmosphere because of that dissolved carbon dioxide, they leave the atmosphere, and it can occur as a gas form or as a liquid form. And so we call that precipitation, of course. And so there are two different terms about whether it leaves as a gas or leaves as a liquid. We call it wet deposition when it's leaving as a liquid, such as in rain, fog, or snow. And I know fog kind of seems like a gas, but it's actually a mixture. We call it a colloid when there's two different phases in a mixture. It's a solution of gas and liquid. So it's foggy because it has liquid gas particles, liquid particles of water mixed with the air particles, and that's the fog. So it has liquid particles in it. So anything that's liquid going down to the earth is wet deposition, but you can also have gas particles directly settling onto the earth, coming out of the atmosphere, deposition. Wet deposition versus dry deposition. All right, and then big surprise, we've talked about some of these pollutants before. A big source of the acidity when you talk about dry deposition is what we call NOx and SOx, so nitrogen and sulfur with oxygen. So we've talked a lot about NOx in the past. Just kind of an interesting thing I wanted to show you with kind of evidence of how this is affecting, and it's affecting the United States in a very different pattern. Much more acidic measurements, I guess we can say, from the East Coast as opposed to the West Coast. I always thought this might be a good EE investigation. It could be because this part was settled more, and this is where your Industrial Revolution was kind of centered, which probably has a lot to do with it. But it also rains a whole lot more over there. And so there's probably more of a problem to begin with, and then it's actually being brought from the atmosphere down to the earth a lot more often. So a lot more acidic on the East Coast as opposed to the West Coast. All right, so now there's two different things that we can look at, two different ways that this can kind of, this problem can be created in the first place. So a primary pollutant would be something that is directly released into the air. So that's our NOx and SOx. And then the secondary pollutants means that something else has to happen in order for it to be a problem, like our acid rain. So we have to actually have the acid in the air in the first place, and then it needs to get absorbed into the water and brought down. So we would call that a secondary pollutant, because there's a second chemical reaction that happens. Two main types. And these are in terms of source of the problem. All right, so we're first going to look at SOx, meaning sulfur oxides. So there's a couple different places sulfur oxides can come from. First, naturally from volcanoes, And the notes, the note takers mentioned the volcanoes, but they didn't mention the organic matter. I would add that in there because we're going to see that come up again later in the notes. So any kind of decay, like when a living thing dies, trees decaying, anything like that, is also going to release sulfur. And sulfur oxides tend to have a very specific, like rotten egg smell. So rotting kind of associated with because of that sulfur oxide. It can also come from something we call more of a man-made source. I want to warn you before I get into why about terminology IB is really weird about here. We've talked about, for example, like synthetic elements before that are man-made, or maybe you've heard of like synthetic fibers, man-made fibers for clothes. Man-made and synthetic are synonyms, but this new term here, I'm not going to pronounce this right, anthropogenic, whatever this term is, it's a synonym for man-made, but anthropogenic and synthetic are not synonyms. It has a completely different connotation to it. When something is synthetic, it's like we intended to make that atom, or we intended to make that fiber, where we are not intending to make pollution. So that's kind of like an accident that we've made it. So just the idea that it is man-made, but not on purpose, is more the meaning for anthropogenic. So be careful to use just this word specifically and don't use synthetic. Okay, anyway, so we're accidentally making some pollutants when we burn coal. That also contains sulfur. Coal comes from an organic source, right? Talking about like natural decay to make coal. So it actually is responsible for a large portion. 50% of all of the SO2 emissions come from the coal burning. So also some other, I'm not entirely sure how some of this stuff works, but smelting, like whenever you're making some of these other fuels, I'm not entirely sure what the process of smelting entails, but it is like fuel making that will then form the sulfide. So we're getting SOx into the atmosphere, which is bad. One of these two ways. Again, just to kind of point out another trend that might tie into the acid rain, a lot of coal production being occurring in the East Coast as opposed to the West Coast. So kind of make the connection there with the map we looked at earlier where we saw a lot of the acidic damage being done on that side. So definitely a correlation there. All right, why is it bad? Big surprise, it hurts your lungs. So it's a respiratory irritant that can lead to any kind of infection or irritation in your respiratory tract. So that's why we're trying to avoid it, trying to improve our health. All right, so yeah, the sulfur dioxide, and this is actually the sentence that's in the note takers, sulfur dioxide can actually occur from volcanoes and those organic decay, and it's produced industrially, basically burning coal. So here are the reactions, and you got to know your reactions. So sulfur reacts with oxygen to form sulfur dioxide, and then that sulfur dioxide can then become further oxidized to form sulfur trioxide. The sulfur trioxide is more of the problem. We also can have the SO2 reacting with water to form sulfurous acid. And then the more dangerous, because it's a strong acid, the SO3 could react with water to form sulfuric acid. So all of these reactions are occurring, like you're forming both sulfur dioxide and sulfur trioxide. Both of these things would be present in the atmosphere. And then when we have water particles around, like rain particles or water vapor in the air, then it can kind of absorb or react with either one of the sulfur dioxides or sulfur trioxides to form the acid. And the only reason I say the trioxide is more dangerous is because it forms a strong acid. SO4 is one of our strong acids. It's going to 100% dissociate. We're going to get a lot of hydrogen particles. Good to go? Okay. So then the ways that we can kind of address this, reduction, not chemical term, but just like how to reduce the problem. We could try to prevent the sulfur from getting into the atmosphere in the first place by removing it from the fuel. And we're going to look at individual slides on each of these three things here in just a second. So the first thing that they call hydrodesulfurization is removing the sulfur from the fuel in the first place. We can also scrub it with a base, kind of trying to neutralize it. And then we can also make it so that it's going through combustion kind of as it's reacting. So it's on this bed of combustible material. So let's look at these one by one. So hydrodesulfurization, water removing sulfur process. Oops. There we go. So the sulfur is going to be in the coal. So whatever the metal sulfide is that's kind of absorbed into the coal. So for example, the iron sulfide, it can be mixed by crushing up the coal, mixing it with water, so that the water then will attract the whatever the metal is, especially with transition metals being very attracted to form complex ions with water. Like we've talked about that before, the complex ion thing where they act as ligands. So that's kind of favorable to happen. We just need to expose it. Think like collision theory. We need to crush up the coal, mix it with water so that it has the opportunity to form those ions. And then that will be pretty spontaneous. So the sulfides are going to then sink once they're mixed up with the water, and then you can clean off the more purified coal and use that. And that way, if you burn it in the pure form, then you're not releasing the sulfur. You've like removed the sulfur before it can get to the air. And then in terms of oil, it can be refined, and when that happens, kind of same process, but with oil, it's going to form hydrogen sulfide. But it's still going to sink to the bottom, and then you get your pure coal on top, or pure oil on top. All right, then we could have the alkaline scrubbing. So this is used a flue gas, I hope I'm saying that right, to desulfurize or remove the sulfur from it. So that sulfur dioxide can be removed from the exhaust of coal burning plants by scrubbing it with an alkaline slurry of limestone or lime. And so there's the reactions for both, because depending on like what part of the country you're in, what you can get access to use, either one of these things work. Calcium carbonate or calcium oxide, the common names for which are limestone and lime. And so we use these in the slurry, and I have a picture of it on the next slide, or actually let me just go ahead and go back. So it's this little metal container, and so the whichever one, limestone or lime, goes in along with whatever the thing is that you're trying to clean the sulfur out of. And then you have lots of little metal places in here for it to be able to kind of settle on and react with each other. The clean gas goes up, and then the sludge of the sulfur compounds comes out the bottom. So the limestone or lime are reacting with the sulfur compounds to form CaSO3. And then if you're doing it with the limestone, you also get carbon dioxide. And then that CaSO3 is then oxidized to form CaSO4. And that solid sludge will come out the bottom. And believe it or not, we can actually even recycle the sludge, as gross as that sounds, sludge. It can be used to kind of insulate a landfill. Like the trash doesn't just get piled up with on trash on top of trash on top of trash. They put this sludge on in layers to kind of control the smell and the decay and everything. So it can be used as kind of landfill liners and fillers. And then it can also be used to make plasterboard, which you may know more as drywall, like what your walls are probably made of behind, like that kind of flimsy wall. So lots of recycling. This seems like a very good strategy. Can be a little expensive though. And then this is a more modern method, apparently, to use this fluid bed for combustion, where the limestone or the stuff that we would be used to remove the CO before it, just to go ahead and have the reaction on it with that limestone present. And then as it's burning on the bed, the sludge is then coming off. So it's kind of just like doing it all in once instead of as two separate steps. Sounds like that might be a little more complicated though. Those are main three methods. All right, let's move on to NOx then. That was all about SOx. On to our nitrogen oxides. So big problem, and probably another reason why this is kind of affecting the East Coast a lot more, is this comes from electrical storms. We don't have a whole lot of storms out here, right? So that energy can kind of catalyze things that are in the air, and then things, biological process. It's just kind of a side byproduct, I guess I should say, of life. Also, we can make it. And again, we have this fancy term, anthropogenic. Don't use synthetic. So in a combustion engine, like our cars, assuming you don't have an electric car, but like a regular traditional gas burning car, is going to run on a combustion engine. So when we get the temperature up there high, we're able to have this nitrogen react with oxygen. And again, at high temperatures, have enough energy. And then you form a nitrogen monoxide. Oops, sorry, too fast. All right, and again, same exact problem, irritant to the respiratory tract. So that's the big health drawback. That's why we do not want these NOx substances in the air. All right, so they can occur naturally from the electrical storms or the biological process, and it can also be produced for internal combustion engines. And I don't know why they specifically mentioned jet engines. Even your car engine is going to do this. So it's a pretty endothermic process, which is why it said at high temperatures earlier. And if you have more oxygen available, sometimes you can also form nitrogen dioxide. And I don't have the exact enthalpy for that. It's still at high temperatures. So then once you have either nitrogen monoxide or dioxide, that's why it's the X, because it happens to either one, then that can be oxidized. Oh, this is just another way to form NO2. That can be oxidized. And here's the problem. The nitrogen dioxide is then going to react with water to form nitric and nitrous acid. Oops. So the NO2 reacts with water, and it forms both NO3, which is our strong acid, and the weak acid of HNO2. And there's even one more way to form strong nitric acid, and that's if the NO2 reacts with oxygen and water at the same time, then you can also get nitric acid, which is our strong acid. And again, this is in the atmosphere, so you have the presence of all of these things. So it's just a matter of collision theory of which reaction is going to occur. And you're going to get these acids. The strong one will produce a whole lot of hydrogen ions, and that's the problem. All right, everybody got these? Okay. So then we're going to look at how we can reduce or kind of mitigate our effects of the NOx. How can we kind of reduce how much of that is being put into the atmosphere? So first we have the catalytic converter, and I have a more detailed slide on that in just a minute. The other thing we could do is lower the temperature so that we don't have enough energy. Remember, we looked at how endothermic it is. So if we try to reduce the temperature and have a way to get energy without having to have that high temperature combustion, then we don't have the side effect, because then this reaction can't happen, that first initial creation of the NO. And one way to do that is to just kind of recirculate your exhaust gas. So it takes longer. The engines are typically not as efficient or as, I guess, fast might be the term, but it would prevent the formation of the NOx. And then the other thing is, if it's used in transportation engines, then let's find a different way of transporting ourselves. Like, let's not use the gas cars. Let's use the electric cars or the electric train or whatever. So kind of just avoiding the need for the combustion engine is that idea. So first on the catalytic converter, the hot exhaust gas is going to be passed over some kind of catalyst. And these, I guess, are the common ones. Platinum, rhodium, and palladium transition metals. And they're going to oxidize the carbon monoxide and any unburned VOCs. We have seen this term before, but it's been a while. It stands for volatile organic compound. Volatile organic compound. So your hydrocarbons that are very easily turned into gases. Volatile means it likes to be a gas. Organic hydrocarbons, compound. So those are going to completely react. Basically, it's good at oxidizing the carbon, and that's going to catalyze this reaction. So the carbon monoxide reacts with nitrogen monoxide to form 2 carbon dioxides. So it's kind of removing our oxygen and preventing it from being NOx, which is nitrogen. And then I don't have more detailed slides on these other 2. It's just that we can lower the temperature so that it doesn't have enough energy to combine, or we can find another way to get around. That is it. All right. Next thing we're going to look at is a set of reactions, a mechanism, including free radicals. Ready? Okay. All right, so remember, you need to know reactions in general, and this was specifically on their slide to memorize these particular reactions. So I might star this section on the mechanisms. We're going to look at how NOx and SOx are converted into acid, and we're going to look at the mechanism that includes a free radical called hydroxyl. So you might recognize OH is like hydroxide when it's the -1 ion. So it's just looking at it as a free radical. And remember, when you see the little dot next to it, that's representing the free radical. So first, the hydroxyl free radicals need to be formed. And so the way that that occurs is water reacts with ozone, and that's going to produce a couple of the hydroxyl free radicals, and then the ozone is converted into oxygen gas. Remember, we talked about how ozone can be problematic. So at first, this kind of seems like a good thing. Or, so this is a second way that this could occur. The water could react with an oxygen free radical. And we've looked at the mechanisms of how ozone becomes oxygen before, and that's where your ozone free radical is coming from. That's why it's present in the atmosphere. So if the water happens to bump into that instead of an ozone molecule, you still get this hydroxyl radical. All right, so this is how hydroxyl gets in the atmosphere. So once it does, it can react with the nitrogen. We're going to look under this last part at 4 different reactions: hydroxyl with the 2 NOx and hydroxyl with the 2 SOx. So these are 2 of 4 reactions under this last section. Hydroxyl can react with NO2 to form NO3, or if it reacts with just NO, then it's just NO2. And nitric acid is the strong acid, nitrous acid, weak acid. So this is the nitrogen reactions. Now let's look at our sulfur reactions. So first, the hydroxyl would react with the SO2 to form another really complicated free radical. Basically, it all just combines and it's still a free radical. And then once that's oxidized, then you get the hydroxyl free radicals and the SO3, which is still not an acid yet. But remember, the SO3, this was one of our reactions we already had in another section. SO3 likes to react with water to form sulfuric acid. And that's a strong acid, so we're going to have lots of hydrogen ions. And this is the last of the reactions. I know there's quite a few of them. Next, we're just going to look at some of the harm that acid deposition causes. All right, ready for the last page? Okay, So we're going to look at 4 big effects of acid deposition, and the first is on vegetation. So we've talked about damage, or I mentioned earlier, the damage on rainforests and things. So whenever we start to see this type of kind of eating away of the leaves, there's actually a little more to it. It actually starts in the soil. The increased acidity in the soil is going to leach, meaning kind of absorb different nutrients like calcium, magnesium, and potassium. This actually ties back to the activity series. Remember with single replacement reactions, the thing that wanted to replace the cation had to be stronger. Well, hydrogen is pretty low on the activity series. So there are a lot of metals that it can replace, or that can replace it, I should say. This calcium, magnesium, the potassium, they would all be happy to replace hydrogen in whatever acid is in the soil. Meaning now they're not in the soil for the tree to absorb. So it's kind of stealing that. And then you're also gonna get hydrogen gas being released, but that's really not a problem. It's more of the fact that the metals are now missing. There's a specific one that's an additional problem when it really reduces the magnesium. So once the magnesium replaces it, then it's going to also affect how the chlorophyll are able to go through photosynthesis. It's going to kind of kill off the chlorophyll. And then you don't have as many things making food for the plant. All right, so we can see, especially in this picture here, that there's a lot of trees out there that have been affected by the acid rain. And so what you're going to see when this soil stuff happens is it's not able to grow because it doesn't have enough food. It doesn't have the nutrients. And so you're going to see the treetops thinning and yellowing and loss of leaves. And there's an incorrect assumption here that it's the rain falling on the leaves that eats away the leaves. That's not how it works. It's messing with the way that the tree gets its food and it's then not able to grow. All right, and then there's also an aluminum replacement that can happen. So when it's leached from the rocks, then the aluminum that's now in the rainwater is going to damage the roots and prevent the tree from taking up water. So it's kind of screwing up all of the access to food, water, everything, so the tree can't grow. Bad for vegetation, meaning any kind of plants. It's also a problem for lakes and rivers. So we just talked about how it can leach the aluminum, which is very common in soil and rocks and stuff. So if we have a lot of that aluminum in the water, then that's going to be a problem for the fish. Also, as the water itself gets into these other water sources, like the rain, the acid rain is then in the lake and in the river, that itself is going to affect the pH significantly. And that's a big problem for the life in the lakes and rivers. So below a pH of 6, then that's going to start affecting fish like salmon and minnow, as well as the larvae and algae like plant life and baby bugs. And for example, snails can't survive less than a 5.2. So they're very, very sensitive. And once we start putting in acids into the water, you're screwing up that pH. You're going to get killing off of all the little things. And then as you know, that has an effect on like a food chain. It's going to work its way up. So still in the lakes and rivers, below a pH of 5, a lot of your microscopic animals are going to disappear. A pH of 4, there's pretty much nothing in the lake that's going to be able to survive. All right, there's another weird phenomenon that comes up here. It says the nitrates present in acid rain can also lead to there's so many words I can't pronounce in these notes. Eutrophication, let's go with, which basically means that the organic compounds that are all dying are now going to also affect the pH. Because remember we talked about, I actually told you, read it in your notes, that organic decay is going to be a production of I believe it was the NOx. No, it was the SOx, sorry. So this organic material that's decaying is also going to produce sulfur oxides, which is problematic. This actually is kind of food for algae. So what can happen is, although a lot of these other animals are dying, certain types of algae-like plants can actually thrive in this environment. And you would think, well, okay, if we have a lot more plants, that would be good for the ecosystem, right? But it actually is like too good that the plants become more dense. They grow so much that it chokes up all of the oxygen. Like any plant that or animal that was in that area can't get any of the oxygen or the nutrients that it needs, and it kind of chokes out any other life. So it's kind of an interesting phenomenon. You might Google it if you have some free time. All right. The other thing is it's going to start eroding things like our buildings. So it's going to start kind of compromising the integrity of the things that we build. Here's just an example on a statue, which is just a good example to show you how the effect works. Like it's kind of eroding and wearing down. This is actually more of a problem if you start thinking about like building supports and foundations and bridges, and you know, starts doing this to the bridges, then the bridge is going to collapse. Yeah, it's sad that the statue is eroded, but that's not going to, you know, kill anyone. So we're worried about it with the foundations and the bridges and stuff. All right, so how does that work? This is not a reaction that you need to memorize at all, just kind of to show you how it's working. It's washing away, it's reacting with the sulfuric acid in this case. So calcium carbonate, remember our limestone, I guess this is actually, limestone reacting with the acid forms a calcium sulfate. It's also producing carbon dioxide and water. But the idea is that whereas the limestone was stationary as solid, now that we have this aqueous substance that washes away. So that's kind of the takeaway of this reaction. The other problem is that some of the salts that are formed, like once this calcium sulfate washes away, some things that are formed can also be precipitates. These salts are going to then settle into stone, and then it's like the bricks, for example, were maybe built to be a certain spacing apart, and now you've got other stuff kind of getting stuck in the cracks, and it's going to start making things want to kind of fall apart once you get like extra stuff in there that wasn't supposed to be there. So it's hurting our buildings. And then last thing, we've mentioned some health risks already. We mentioned respiratory illness a couple times because the NOx and SOx that are in the atmosphere are going to irritate as you're breathing that in. It's irritating the mucous membranes in general. So that's like what your nose and your lungs are all like covered with. In acid water, there's also a possibility, or I guess probability, of poisonous ions. Like our body doesn't have a tolerance for certain metals. Some metals we use, some metals we don't. Like zinc is good for us. Copper and lead, not so much. You might have heard of like lead poisoning, where they didn't know a long time ago that it was bad to use lead in paints. Well, we use a lot of these things for wires and pipes and things. So if hydrogen is so low on the activity series, it's also going to leach those copper and lead ions and bring that into our water table, which can lead to like bad water, poisoned water. And then aluminum, which we mentioned is on like rocks and soil and stuff. So if we have that in the water, then that actually has been linked to Alzheimer's disease. And who knows how many other kind of little diseases with some of these ions that we're not supposed to have in our body. So, and it all goes back to that acids have that hydrogen that's super low on the activity series. So whenever you have the acids, you're going to be absorbing all these other ions. All right, so we've got 4 main categories of problems. Now let's talk about 3 specific ways to lower or counteract the effects of the deposition. So 1, and we went through several details on how this would work, we can try to lower how much NOx and SOx we have in the environment. So we talked about things like catalytic converters. We talked about ways to remove the sulfur from the fuel before you burned it, or how to burn it on that fluid bed so that it's kind of absorbing the sulfur, taking that out before you get into the atmosphere. All the things that we went over on pages 18 and 19. The other thing we could do is to try to find another way to produce energy, because obviously if the NOx and SOx is coming from coal, if we could find a different way to not have to use coal to get fuel. So this is part of our whole energy crisis. Is there a way, a cleaner way to kind of reduce our carbon footprint? We would also be reducing the NOx and SOx in the atmosphere. Right? And then the last thing is trying to prevent the harmful effects in the lakes. So say we've failed at the first couple, we've got NOx and SOx in the atmosphere. This is more of a reactive way to limit the effect. If we know that this calcium oxide, like the lime or limestone, is used in preventing it from getting there, well, once it's there, if we add it, it's still going to neutralize the acidity. It's still a base. And so they're just talking about adding, like if you're seeing the pH of the lake increase, adding the base to kind of neutralize it and to react with some of that acid instead. Of course, with the pH, the things in the lake being so sensitive to the pH, you got to be really careful with this too. So it has limited uses because you can't make it too basic either. Yeah. All right, and that does it for all of notes F. Well, that also finishes all of our notes on acids or bases and all of our notes together. And I'm very sad. So I hope you had fun. Let me stop this recording real quick.